Okay, good. So, what I am going to discuss today is this um, existence of bound entangled states entangled Gaussian states. Okay. So, before going into the details of this, so let me give you some trivial example of bound entangled states in infinite dimension. Okay. So, this is trivial case of bound entangled states in infinite dimension. Okay. So, let us take uh, a state bipartite state rho a b, okay. And this is a bipartite state. This is a bipartite state on, let us say, H A tensor product H B, where both these are finite dimensional. Okay. So, the dimension of H A, let me call it as d A, this is finite. So, plus infinity, and similarly dimension of H B, which is d B, this is finite. Okay. Both of them are finite dimensional. And let us consider a bipartite state rho a b, and let us assume that this is bound entangled. Okay. So, rho a b is bound entangled. What does it mean? It means that, let us say there are two parties, Alice and Bob, and they share many copies of this state. Many copies. Okay. So, this is with Alice's lab, this is in Bob's lab. So, in fact, in principle it can be infinitely many copies, and then Alice performs some operation here, communicates to Bob, Bob performs some operation on his system, communicates to Alice, so on and so forth, or it can Bob can also start first. So, you apply LOCC, local operation and classical communication, to get a state like this, to get some entangled state like this. So, which I call phi plus A B, maybe it is, let us say, m copies. Okay. And so, here let us say it is n copies. Okay. So, the point is that this is your maximally entangled state. So, phi plus is 1 upon square root of d, sum over j is equal to 1 to d j j, this is A B, and d is equal to minimum of d A d B. Okay. So, the question is that this m by n, limit n tending to infinity, this is what will provide you a lower bound on the distillable entanglement of rho A B, how much you can distill. So, if it turns out that this is 0, okay, over all LOCC, whatever you choose, it does not matter. Okay. So, it means that this m should be 0, you cannot have even a single copy of this maximally entangled state. Okay. So, then we say that this is a bound entangled state. So, this will tell me that rho A B is a, this is entangled, of course. I mean, this you should have clear in mind. This is entangled, otherwise it does not make sense. This is entangled, but this is a bound entangled state. Okay. So, it means that by LOCC, whatever be the number of copies of this entangled state you take, you cannot distill anything out of it. Okay. Right. Now, one can show that if this is I am talking about finite dimension for the time being, I will go to infinite dimension later. So, if rho A B this is entangled, but it has a positive partial transposition, then it is definitely, this will imply that rho A B is bound entangled. Okay. Why? Because in this case, if you try to apply such a process, you cannot generate even an iota of this maximally entangled state by LOCC. Okay. So, even though it is entangled, you cannot distill anything out of it. So, any entangled state having positive partial transposition is a bound entangled state by definition. Okay. One can also prove this thing rigorously, but yeah, any dimension, any dimension, any dimension. Yeah. In fact, the idea is that you take many copies of this state having positive partial transposition and then try to project it. So, let us say I take this is an entangled state, okay, is entangled with rho A B T. You can take T A or T B, does not matter, with positive partial transposition. So, what I can do? I can take, let us say, n copies of this, okay, large number of copies, and then what I do is, so this is okay. So, what I do is I project it. So, let us take this projection P of A n, which is a projection from H A tensor n to C 2. Okay. This is a projection. Okay. So, projection means if I take square of this, it will be same as this. Okay. And similarly, P B n, which is a projection on n copies to C 2. So, both of these are projections, right. So, now if I apply this projection P A n tensor product P B n, okay, this is also a LOCC. I mean, CC part is not there, but that is okay. And of course, this is not trace preserving, but in principle that we can consider later, fine. So, what will happen here if I do this projection? I will get some state, let us call it as sigma tilde A B. This is this is what? It is a 2 QB state, right? Of course, unnormalized in general. Do you agree with me? Because I am projecting it. Okay. So, this is a 2 Q and it has to be a valid unnormalized state because of projection. Okay. So, this is a 2 QB state. So, the idea is that if your state, original state is distillable, that means you can distill something like this, then so rho A B is distillable, it means that this sigma tilde A B Okay. So, let me maybe I should put n here also because of this n. So, this is entangled. Okay. So, this is a 2 qubit state which is entangled. Is it okay, right? Because unless this is entangled, you cannot have a maximum, I mean some pure state out of it which is entangled, it is not possible. So, this has to be entangled, right. And in other words, so this means that sigma tilde a b n, if I take its partial transposition, let us say b, this is not positive semi definite, right. So, entanglement means this thing for 2 qubit case. For some n, I do not know what n it is, but for some n this has to be the case, okay, because this can be n can be 1, 2, 3 whatever, but this has to be the case. Okay. So, the point is, if it is true for n is equal to 10, it will be true for higher values of n also. No. So, if you cannot find out any n less than 10 for which this will be satisfied, that means you will not find out. So, n is the minimum value, n is equal to 10 is the minimum value. Of course, because distillation considers many copies. Okay. So, if it happens for n is equal to 10, then we say that this is 10 copy distillable.
That n goes to infinity quantity.
Yes.
That will be zero, because for n greater than 10 you cannot distill it.
See, if n is equal to 10, you can do, of course, you can do for n greater than 10, not n less than 10. Right. So, here you see that this notion of partial transposition comes into picture. So, in fact, by reverse you can show that if the original state has positive partial transposition, no such thing can happen where this is, because under LOCC positivity of partial transposition cannot go to negativity of partial transposition, it cannot happen. Negativity of partial transposition can go to positivity of partial transposition, but the opposite cannot happen under LOCC. Okay. And this is projection is a special case of LOCC. So, therefore, acting on if rho a b is having positive partial transposition, its n copies will also have positive partial transposition, and if I apply this, I will get a state having positive partial transposition only. Okay. So, therefore, entangled state rho a b entangled having positive partial transposition means rho a b is bound entangled state, right. Okay. And yeah, several examples of this, but let me give you just one example where you can. So, this is called tiles UPB, unextendable product basis. So, let us say I take dA is equal to dB is equal to 3, okay, and let us take this state. So, this is like tiling your floor. Okay.
So, what does UPB stand for?
Unextendable product basis. So, let us call it as 0, this is 1, this is 2, this is 0, this is 1, this is 2. Okay. Right. So, this state, let me call it as capital psi 1. So, capital psi 1 is equal to 0 A. So, this is on A part A and this is on B part B. Tensor product 1 by root 2, this is 0 B minus 1 B. Okay. So, this is the state psi 1, 0 A tensor product 0 minus 1 by root 2. Let us call this as psi 2. So, psi 2 is equal to, it will be 1 upon root 2 0 A minus 1 A tensor product 2 B. Okay. This is your psi 2. Let us call these as psi 3. So, psi 3 is equal to 2 A tensor product 1 upon root 2, this is 1 B minus 2 B. This is your psi 4. Psi 4 is equal to 1 upon root 2 1 A minus 2 A tensor product, this is 0 B. Okay. And then psi 5, the fifth one is the entire one. So, 1 upon root 2 1 upon root 3, this is 0 A plus 1 A plus 2 A, maybe I will write here because it may be difficult. So, then I will write here psi 5 is equal to 1 upon root 3 0 A plus 1 A plus 2 A tensor product 1 upon root 3 0 B plus 1 B plus 2 B. Okay. So, these are 5 product states in C 3 tensor C 3, right. Okay. So, these are 5 product states in C 3 tensor C 3, and you can check that all of them are orthogonal to each other, right, because for example, this one psi 1 is orthogonal to psi 2 because it is via the B side, right. Similarly, psi 1 is orthogonal to psi 3 via A side, so on and so forth. So, all of them are orthogonal. Now, in C 3 cross C 3 we have bases consisting of 9 states, right. These are 5 product states. Question is, can I complete, this is incomplete orthogonal basis, can I complete it to a 9 dimensional product basis, orthogonal product basis, right. And the answer is no, you cannot find out. So, there is, so therefore, there is no product state which is like like this one alpha 0 A plus beta 1 A plus gamma 2 A tensor product, this is alpha prime 0 A 0 B plus beta prime 1 B plus gamma prime 1 2 B, okay, which is orthogonal to psi 1 up to psi 5. Okay. So, you can verify that no such product state exists, right. So, in other words, if I take So, let us say S is the linear span of this 5 dimensional subspace. This is 5 dimensional. So, let us take S as the linear span. So, therefore, dimension of S is 5. So, let us take S orthogonal, which is orthogonal subspace, orthogonal subspace, okay, or you can orthogonal subspace to S. So, the dimension of S is, so the dimension of S perpendicular is 4, right, because it is 5, it is 4 dimension of S perpendicular. So, in this subspace, 4 dimensional subspace, there is not a single product state. Is that correct? Because there is no product state which is orthogonal to this. So, therefore, in this subspace, 4 dimensional subspace, there is not a single product state, right. And so, if I take 1 by 4 projection on this S perpendicular. So, that means I take the projection on this 4 dimensional subspace, right, and let me call it as something like rho bound. So, you see that this is the identity on this 4 dimensional subspace S perpendicular, and I multiply by it 1 by 4 to make it normalized. So, then this is a valid state acting on the C3 tensor C3, and this state has to be entangled, because there is no product state in its support. So, therefore, it has to be entangled, and you can verify that rho bound partial transposition T A or T B is greater than equal to 0, because this is what, this is basically identity on the entire space minus projection on these sum of projections on these 5 product states. So, therefore, it has to be, in fact, you can show that this is equal to this. Okay. So, therefore, this is positive semi definite. So, this is a state which is which has positive partial transposition and it is entangled. So, therefore, it has to be bound entangled. Yes. So, I take the projection on this 4 dimensional subspace which is orthogonal to S, okay, and then I multiply it by 1 by 4 to make it a density matrix, right, which I call rho bound. Now, if I take partial transposition of rho bound, then you will see that it will be same as itself, okay. Why? Because what is rho bound? Rho bound is 1 by 4 identity on this 9 cross 9, identity on this entire thing, minus sum over j is equal to 1 to 5 psi j, right. And if I now take partial transposition, this will not change, and these are real product states, they will be same as themselves. Okay. So, therefore, this is a yes. Yeah, because if I take rho bound partial transposition, it will be this partial transposition will be same as this, and partial transposition of each of these product state, because these are expressed in terms of real coefficients, they are same as themselves, okay. It will not change under partial transposition. So, therefore, this is equal to rho bound, right, and therefore, this is so therefore, this is non-negative partial transposition. Okay. So, this is a generic method of designing bound entangled state. There are other ways also. This can be generalized in higher dimension, whatever. Any.
So, this is not a unique construction.
No. I mean, you can have these tiles in different ways. I have taken a particular superposition.
But so the number is fixed. It will be always 5, or
in this format it is 5, but you can have bound entangled states in other form also.
No, like this UPB. So
Unextendable product basis, it is in 3 cross 3, it is not necessarily only 5 product space, it can be more than 5 also.
for some different construction.
Yes. Okay. But this is just one example, okay. So,
Is there a way to explicitly show that the n to n ratio,
mhm.
the large n limit, in this case goes to 0?
In fact, you know, you can try with LOCC to do that, okay, but because this is you know, it is PPT, no LOCC will work, okay, nothing will work. So, so for PPT states, this distillation question does not arise. So only it will arise when you have an NPT state which is also bound in time. But we don't have any such example. People think that they should exist, and there are strong evidences for that, but so far we don't know. So for PPT state, we don't have to do anything because it is evidently undistillable or non-distillable. Okay, so let us take rho AB, a PPT. When I say PPT means positive partial transposition, bound entangled state. So separable state has PPT, bound entangled state also have PPT, can have PPT. Okay, so bound entangled state in, let us say it is to make our life easier, CD tensor product CD. Okay, I mean it not necessarily same dimension, right. Now let us take say 2 copies of this, 2 copies of this bound entangled state. Then this is again PPT bound entangled state, bound entangled state, right. In this is CD 2 copies tensor product CD 2 copies. Do you agree with me? I am taking 2 copies. So, this is again it has PPT with respect to one party like this party or this party, and of course, it is a bound entangle, because had it not been bound entangle, you could have distilled something, right, which goes contrary to this assumption that this is a bound entangle state.
Define the partition there to define partial transposition.
Yeah, yeah. So, when I say 2 copies means it is, so rho, let us say AA BB, this is 2 copies, and then you take TBB or TAA, yes, 2 copies of A and 2 copies of B.
Be part of the both.
Yes, 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 yes. So, in this way you can show that rho AB, if I take n copies, this is PPT bound entangled state. You start with a single copy of PPT bound entangled state, take n copies, again this is a PPT bound entangled state, right. Okay. So, now, so this is in CD tensor n, tensor product CD tensor n, right, and this is what, this CD tensor n means this is basically C d to the power n tensor product C d to the power n, right, is not it? Yeah. So, you see that if I take n to be very very large, then this will amount to infinite dimension. This will also amount to infinite dimension if I take n to be very large, right. Okay. So, you see that by this way you can construct a PPT bound entangled state for infinite dimensional systems. right. But of course, this is trivial, this is you have not used any anything specific to infinite dimension itself. This is very trivial, and forget about its Gaussian feature etc. I do not go into that details, but this is a trivial way of constructing bound entangled states in infinite dimension, right. Okay. But what we are going to do now is not this trivial way. In fact, this is what in a more sophisticated way it was done, because not just by saying that if I take into infinite dimension and they will correspond to continuous variable system etc. You will have to do little bit of more here. So, there is this work by Pavel Horodecki and Maciek Levenstein. This is in PRL. I will have to see, maybe 2001 or something, I forgot. So, where they basically constructed such trivial bound entangled states in infinite dimension. Okay. I mean, you will have to bring in some notion of continuity here in this dimension, but that is okay. Okay, good.
Cannot just take and tend to
Yeah, it doesn't make much sense. You will have to basically coarse grain this thing. Okay.
get away of this discreteness of the step.
Yes, yes, yes. But nevertheless, this is the idea that you can trivially
Start with some TPT bound state and then just end to infinity by some proper mathematics and you
yes,
end up with some trivial.
exactly, exactly. Okay. So, this paper which I am going to discuss today is this one, bound entangled Gaussian states. This is by R. F. Werner and Michael Wolf. This is in PRL 86, page number 3658 to 2001. Okay. Yeah. So, what they have shown is that so if so here of course one should be careful. I am taking bipartite system AB, okay, where A has or A consists of n number of modes, means quantized harmonic oscillator, and B consists of m number of modes. Okay. So, A has n modes and B has m modes. So, we are considering bipartite system AB of n plus m modes. This is what we are considering. Okay. And here when I talk about rho A B, you understand this is a n plus m mode state of n plus m mode system, and when I talk about its partial transposition, you can either take partial transposition with respect to T A or with respect to T B, right, with respect to one mode versus the other mode. So, that is what we are going to do. Okay. So, what? Yes,
n plus n into m.
total number of modes, it is not n into m, n plus m.
For each, say like for each n, the B can have m states,
No, no, not m states,
m modes.
m mode. So, this is A consists of, let us say, n number of one dimensional quantum harmonic oscillators. A consists of, B consists of m number of one dimensional quantum harmonic oscillators. So, total is n plus m number of quantized one dimensional quantized harmonic oscillators, right.
Like so if A has say 3 and B has also 3,
Yes.
so you have possibilities of 1 1 1 2 1 3 2 1 2 2 2 3.
What is possibility? What is that?
It's not direct product, it's direct sum.
And that y direction. So the space is not a tensor product space.
No, 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 total number of modes. So, total number of so think of it like quantized one dimensional quantized harmonic oscillators.
That's it.
So, how many such quantized harmonic oscillators are there? N plus n.
Okay.
Okay. So, what they have proved is the following, that if rho A B is a Gaussian state, of 1 plus n modes, or you can say n plus 1 modes, it does not matter. Okay. So, if this is a Gaussian state of 1 plus n modes, equivalently n plus 1 modes. What does it mean? So, this is small n is equal to 1, small m is equal to capital N, and vice versa. Okay. If this is a Gaussian state of 1 plus n modes, yes. Oh, I think they cannot speak. I don't know what is their problem.
Sir, can you hear us now?
Yeah, I can hear you. Yes.
Okay, Chandan, you will go ask first.
No, 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 you ask, you ask.
Okay, actually, sir, this bound entangled state.
Yes.
Generally, the entanglement we understood, but the importance of this bound entangled thing, can you just brief us? Like, if they are not maximally entangled, and means you are saying that they are not maximally entangled thing also.
Yes.
So the importance of this, can you just explain, sir?
Okay. So, by, as I said, by definition, bound entangled states are those states which, if these two parties Alice and Bob share even infinitely many copies, by the allowed operation, which is LOCC, local operation and classical communication, they cannot distill even an iota of these bipartite maximally entangled state. Okay. So, that is basically the definition. Now, such states do exist. I have given example, right, of such states. Such states do exist in 3 cross 3. I have given example. We will also see example in infinite dimension. Now, why such states are important? There are several reasons. One is that in order to perform effective quantum information processing, like teleportation, dense coding, or some communication task, we know that maximally entangled states are useful, and even if not maximally entangled state, some amount of entanglement which we can use, which we can distill are useful. So, from this theoretical perspective, it is important to classify which states are not distillable, which are entangled, but not distillable. So, bound entangled states are those kind of states. But the second thing is that even some bound entangled states are useful, it is not that they are useless. Some bound entangled states are useful for several purpose. First of all, one can use bound entangled state to generate secured key, okay, cryptographic key. Not arbitrary bound entangled states, some special classes of bound entangled states can be used for generating secured key. Now, the security of course is compromised because it is not 100% secured, because it is not distillable, but still you can have a good amount of security there. Bound entangled states, although it is not distillable, but this can be useful for enhancing the distillability of some distillable state. So, these can act as some some reference to assist more distillation, more distillable entanglement. So, there are several such things which bound entangled states can be made useful for. And from a theoretical perspective, these bound entangled states are something like in thermodynamics we talk about this bound energy, right. You do work on your system, thermodynamic system, and then you want to extract work from it. Okay. Now, you cannot extract everything out of it. Okay. So, some amount of work we can say it will be lost in the environment or so, that is one thing. But even if it is not lost, you cannot extract everything out of your system, whatever amount of energy you have invested on your system. So, the amount of energy that is there in the system which you cannot extract, that is what is known as bound energy in the thermodynamic sense. So, bound entangled states are something similar to that. So, in order to create bound entangled states, you need some amount of entanglement. So, we say that entanglement cost of bound entangled state is positive, because you need some amount of free entanglement to create it, but you cannot extract or distill entanglement, free entanglement out of it. So, bound entangled states are something similar to bound energy in thermodynamic setup. Okay. So, yeah, so it is not useless, it is useful, but on the top of that we should understand, we should characterize what entangled states are bound entangled and what are distillable, in order to figure out what sort of states we are going to use. Is that fine?
Yes, sir. Thank you.
Thank you. Yeah, Chandan.
I didn't have any question. I was just trying to get connected for Sanam and one.
Oh, okay. Okay then. Yeah.
Do they act as a catalyst during distillation or
No.
through some other, like how do they come into?
Yeah, so this is called activation of states. You take some some which is distillable state, but it has a limited amount of distillation. So, you take many copies of this, and then you take say m copies of your bound entangled state. So, this is bound entangled, and then you can perform LOCC operation to get something where the amount of distillable entanglement is higher than what you had initially. Yes.
So, rate increase.
They increase. Yes. Okay. So, this is called activation of distillation or distillable entanglement, whatever people call. Okay. So, what I wanted to tell you is that, so if I take this rho a b, which is a Gaussian state of 1 plus m mode or n plus 1 mode, whatever you want to call, then rho a b is separable if and only if rho A B T B is greater than equal to 0. So, this is a Gaussian state of 1 plus n mode or n plus 1 mode, whatever you want to call. So, this is separable if and only if it is having positive partial transposition. So, you remember this Simon's work, Simon's result, which takes capital N is equal to 1. So, 1 plus 1 mode Gaussian states are separable if and only if this is satisfied, right. This is what we have discussed, right. Here it is a generalization of Simon's result. Okay. So, this is their first result, and then they provided a 2 plus 2 mode Gaussian state okay, Gaussian entangled state for which rho A B T B is greater than equal to 0, right. So, this means that this is in 2 plus 2 mode this is not satisfied. You have an example of 2 plus 2 mode Gaussian entangled state which is having positive partial transposition. Okay. So, in fact, they have given one example, but you can generate other examples also. Okay. So, this is their main result, these are the two main results, and so this you may consider it to be generalization of Simon's work. Okay. Okay. Now, as usual, this is a paper written by Warner and his PhD student. Michael Wolf was his PhD student, and it is a bit a cryptic one. Okay. This is the usual practice of Warner. If you read his paper from a physics perspective, it is a bit cryptic. Cryptic in the sense that lots of things are not written. You will have to dig out and all those things. Okay.
You also mentioned that this idea of bound entanglement or disclaimable entanglement kind of is analogous to the idea of work that we can extract from the thermodynamics.
This is analogy. There is it's difficult to come up with a quantitative analogy. This is a qualitative analogy, in the sense that let us say you have disclaimable entanglement. Can you use it to extract work? Because that is the idea, right? I mean, if you have disclaimable entanglement, to extract some work. Okay. Okay. So, that people have given, but it is not a generic one. Like, so basically, if disclaimable entanglement, it means of course you have quantum correlation, otherwise you cannot do. So, from quantum correlation, people have given schemes how to extract work, not for generic one, certain specific example. See, extraction of work in the thermodynamic sense is very typical. I cannot say that any form of energy can be considered as work. It has to be some ordered form of energy. Okay. So, this Antonio Assin and other, they have given some examples where disclaimable entanglement can be used for extraction of work. Bound entangled states, I cannot say that that this is an analogy. This
Mathematically, the analogy holds true. Then, like
mathematically, again, it is not. I won't say it is a proper mathematical analogy. It is just, see, as I said, if you want to say that from a bound entangled state, no work can be extracted, right. So, that is the idea, right. So, that people have tried, like Sandu Popescu and other, they have tried some time back, but it is difficult. I mean, so far it is difficult. Maybe at some point of time one will have a better idea. So, there is this notion called ergotropy in thermodynamics, which for closed quantum system you can. So, what you can do is um, you see that let us say you have a Hamiltonian under which your state is evolving. So, you calculate the average energy initially, right, and then calculate the average energy finally. So, this difference will be some energy difference, and if you gain something, then so if gain something means what? It means that initially you start with a product state. So, let us say I have a bipartite system, you start with the product state, system A and system B, you have a product state, right, and so there is no correlation. Now, I can figure out what is the average energy with respect to that product state. I have initial Hamiltonian, let us say Hamiltonian is time independent, you can take also time dependent, right, and then you evolve your state under the Hamiltonian. So, the state will change. Now, what you do is you try to maximize this energy difference, and how will you maximize it? You apply any sort of local unitary transformations on A and B system over which you maximize. So, this is what is known as ergotropy. Okay. So, this is a kind of work extraction. Okay. Now, I mean if so, this notion, if you want to extend it beyond closed system, if you want to go for open system, things will become much more difficult, because there I cannot simply say work, because some amount of energy may get transferred into heat also. So, yeah, so there things are little bit tricky, but yes, there where the people have been trying to relate notion of bound entangled state with the notion of bound energy, but still it is not that quantitative.
In equilibrium systems, like we talk of this, how much work we can extract, and like the mechanics. That,
Yes.
this much work, the entropy is always increasing.
Yeah. So, once it reaches the maximum entropy, you cannot extract work, right.
But the thing is, when you go to non-equilibrium situations, then you have fluctuation theorem instead, which replaces this.
Exactly.
You work at the level of averages rather than working at
Exactly.
absolute.
Exactly.
So is this something similar to it, where you are working in terms of averages rather than working in absolutes?
Yes.
Will
Yes.
there be then a like
Yeah,
an
so
analogous fluctuation theorem? Like
in principle, yes. In
fluctuation
principle,
is-
yes. But again, these people have done, to some extent, people have done, like fluctuation theorem for quantum channels and all that. I mean, basically, essentially, when you talk about correlated state, under evolution, you can think of it as a quantum channel, specific kind of quantum channel. Yeah, so people have talked about these fluctuation theorems of quantum channels. Okay, so but still, I won't say that this is enough to identify or to quantify bound entangled states. See, the problem with bound entangled state is that we know that at least some amount of entanglement is required to create such state. But you cannot distill anything. So, entanglement cost is positive, but distillable entanglement is 0. So, there is always a gap. Okay. So, whether this gap can be assigned to some sort of bound energy or some sort of work, etc., this is something which I do not think people have a clear idea. Okay. Yes, Jatin.
So this maximization was over local unitary.
I think so. Yes.
For ergotropy.
For ergotropy.
So you start with the product state, because these are local unitary, so you will end up with the product.
No. If you use the local unitary on the Hamiltonian might change.
Oh, the Hamiltonian.
Yes. I think not, maybe not local unitary, maybe global unitary also.
Yeah, then entanglement will come.
Yes. Okay.
Also, so these boundary tangle states, you have given one way to construct a boundary tangle state. But is there some study or some literature? Can you characterize all possible boundary tangle states?
So far we don't know.
We don't know that. We just know that they exist, and this is one way to give them. But we don't know.
This is one way means it is not exhaustive way.
Yeah. So there might be some state which cannot be written in because they might not lie in this space.
Exactly. Yes. I mean, you know, even in this UPB formalism, you can have two UPBs in 3 cross 3, each having, let's say, dimension 5. They will give rise to two bound entangled states, but they are not connected by local unitary.
The
They are
entangled
connected by
subspaces.
some global unitary.
The entangled subspaces. The entangled spaces.
Yes.
So these are two disjoint classes.
Yeah, so therefore they are not equivalent bound entangled. Okay. So let me start with this thing, because this is what we are going to discuss. Okay. So, little bit of recapitulation of our Gaussian states, not much, but just to make life easier. So, you know, so n mode state rho is Gaussian. So, for the timing I am not bothered about whether this is bipartite, single system, whatever, it is Gaussian. If and only if its Wigner function is Gaussian, right, which means W rho R transpose is equal to, so R is this vector x1 p1 x2 p2 xn pn. This is an element of r to the power 2n. Okay. So, this is 1 by square root of determinant of gamma rho, then exponential of minus half. This is r minus r rho transpose gamma inverse, gamma rho inverse if you want, then r minus, right. This is the Gaussian state, n mode Gaussian state, right. Equivalently, rho is Gaussian if and only if its characteristic function is Gaussian. What is that? So, characteristic function again R. So, characteristic function is the average of your state with respect to the while operator. So, well, this is here, maybe I will just write here d of R transpose. Okay. This is your d of R transpose. So, what is d of R transpose? This is basically the displacement operator. So, this displacement operator is, I am writing in terms of real variables, but you know it for complex variable, but that is okay. So, this is the while operator. and this is basically exponential of minus iota r transpose, then omega, then r. And what is this omega? Omega is I sigma y plus I mean direct sum I sigma y n times, right. This is the symplectic matrix. So, this is my while operator and this is the characteristic function. If this function is Gaussian, so this means that this is equal to your this one. So, let me write it down. Yeah. So, this is basically, so here you have inverse of the covariance matrix, here it is not inverse, it is direct I m transpose r minus half r transpose gamma rho r. And what is m? M is this one, this is x 1 rho p 1 rho so on x n rho p n rho. Okay. So, this is basically your r vector rho. Okay. This is basically the mean values. Okay. So, this is of course Gaussian, if this is a positive definite. So, I can say that rho is Gaussian if its Wigner function is Gaussian, or equivalently is characteristic function is Gaussian, and in fact, there is a relation between characteristic function and Wigner function. So, Wigner function is the Fourier transform of the characteristic function, right. So, if you do the Fourier transform of the characteristic function, you will get the Wigner function. Okay. Right. So, there are some properties involving this covariance matrix and the symplectic matrix regarding purity of state, but I will come to that later, not now. Okay, when as and when it will be required, I will use that. Okay. So, again I consider n is equal to n plus m. Okay, so it is a bipartite system. So, this corresponds to A, this corresponds to B. I mean A has these many modes, B has these many modes, right. Okay, so, this is I am considering bipartite system. A B, and which is n plus m modes, m mode system. Okay. So, the phase space, yes. So, the phase space is if I look at the phase space, so let me call it as PAB. So, this phase space is phase space for subsystem A direct sum phase space of subsystem B. Do you agree with this? Because this phase space, so this R vector which is an element of this phase space. So, this is basically your x 1 p 1 x n p n, then x n plus 1 p n plus 1 x n plus m p n plus m, right. And now I group this thing up to this this corresponds to the A subsystem, and from here to here this corresponds to the B subsystem. So, therefore, this part corresponds to this phase space and this part corresponds to this phase space, right. So, this is the direction of these two phase spaces. Is it okay? I mean, in fact, this is 2n dimensional phase space and this is 2m dimensional phase space. So, I need okay, what is the time now? So, you can wait and I'll be there maybe for 10 minutes. Okay, yeah. So, this is 2m dimensional phase space, this is 2n dimensional phase space, right. As a whole, this is 2n plus 2m dimensional phase space, right. Okay. So, this I can write it as, so this therefore, I can write R A plus R B direct sum, right. This part is R A and this part is R B, these are the phase space points. Okay, good. So, now if I look at the symplectic matrix, so remember the symplectic matrix alpha beta is, what is that? Iota, this thing is R alpha R beta, right, is not it? That was the case. Yeah, that was the case, because let us say it is x 1 and x 2, x 2 I mean x 1 and p 1. So, then this will be just iota, right, 1. So, yeah, so this is the relation. So, basically what you can see is that I can write this omega as omega A direct sum omega B, and omega A is I mean omega A iota, it is alpha beta, this is R alpha R beta for alpha beta belonging to 1, 2, 3 up to twice n. And similarly, iota sigma b alpha beta is equal to R alpha R beta, okay, for alpha beta belonging to twice n plus 1 up to twice n plus twice m. What about the other alpha betas? All be 0, right. The other choice of alpha beta, this will be 0. So, therefore, I can write in this way, this is also direct sum. Okay, good. Now, if I look at the while operator, d of this is R, so which is d of R A R B transpose. So, I have written the while operator, where is that? Yeah, that one. So, this is exponential of minus iota, this is R A direct sum R B transpose, then omega A direct sum omega B, then R A plus direct sum R B. Okay. This is the definition, right. And then this is what? This is basically exponential of minus iota R A omega A R A transpose rather tensor product exponential of minus iota r b transpose omega b r b, right. Is that clear? Because at the exponential level this is direct sum, but at the operator level itself it will be just tensor product, is not it? Yes or no? Yes? Any doubt?
Tensor product or just a normal product?
Tensor product. Because these are acting on different systems, right? A and B are different systems.
Yes, but the dimension of space like much, so this one is n plus n. Exponential will again be an n plus 1 n matrix. But when you take the tensor product of two exponentials, that becomes n into n. So once the dimension is much bigger, the second last and the last.
Yeah, but the operator level, if you think of, well, it doesn't matter. If I take a, if I take a direct sum, okay, so then it means that this will act on the A subspace and this will act on the B subspace, right? Okay. So, I mean, if I just without, I don't say anything here, I can do that, but we should have in mind that this is acting on A subspace and this is acting on B subspace, right?
Yes.
Otherwise, it doesn't make sense. Because these are commuting operators. So ultimately, if I just write one more state, this will be exponential of minus iota R A transpose R A, because the cross term will not be there. Okay, and then plus this. Okay, let me write it like this: minus iota R B B R B, right? Now, of course, these are what? These are commuting operators, and they are acting indeed on different subsystems, right. So, therefore, even if you write as product, it is effectively tensor product, right.
Okay, but like it's just a way of writing it as a tensor product. It's just a way of keeping track of this subsystem.
Yes, yes, yes. I mean, dimensionally, of course, when you write it as tensor product, it may not match, it will not match, but when you operate it, so I am just writing it in to keep it in mind that this will act on different subsystems. Okay. So, yes, you are right that dimensionally this is, if I write it tensor product, it will not match, but yeah, you should keep it in mind that this is acting on different subsystems. Yeah. I think this is better way of writing it, but you understand that this will act on A subsystem, this will act on B subsystem. Okay, good. So, so this is basically your D of R A transpose B of R B transpose, right. So, your while operator gets factorized like this, okay, right. Maybe I should stop because this fellow has come, you will have to arrange for his talk. So, anyway, so next day what I am going to do is I will prove these two theorems, but before that I will have to introduce little bit more, not much, and then I will prove means one is example, this 2 plus 2 mode, it is just example. The original proof is that one plus n mode. Okay. So, that I will give the proof. Okay. So, I will stop here because we have a talk at 3:30. Okay. Thank you.